Professor Raghunath, Department of Structural Engineering, Annamalai University. A one-year diploma program on damage assessment, repair and rehabilitation of structures is being offered by Annamalai University through the distance education mode. One of the courses included for this program is on deterioration processes in concrete. The intention of this presentation is to throw light on the causes that impair the durability of concrete. As we all know, concrete is a major player in construction industry for quite a long time. Hence, it is very important to impart durability to concrete as much practicable as possible. The causes that affect the durability of concrete may be physical or chemical. First, let us going to see the physical causes that affect the durability of concrete. The causes may be plastic shrinkage, plastic settlement, drying shrinkage, temperature effects, freezing and thawing, fire, corrosion, abrasion, erosion, cavitation, creep, and so on. Now let me present the details regarding. So let me first provide information relating to the physical causes. First cause is plastic shrinkage. When concrete is in a plastic state, there will be loss of mixing water due to evaporation from the surface. The rate of evaporation depends upon the temperature, relative humidity and the wind speed. The water that is lost by evaporation is normally replaced by water that rises to the surface by the action of bleeding. But when the rate of evaporation becomes greater, there is a local reduction in volume. When there is some restraint to this volume change, tensile stresses are induced on the surface. As we all know, concrete when green cannot sustain these tensile stresses. As a consequence, concrete cracks. The cracks due to plastic shrinkage are quite wide on the upper surface and the width of cracks reduces rapidly down the depth of the member. The cracks due to plastic shrinkage may pass through even the full depth of the member. We should also know what are the measures to control this plastic shrinkage. Some of the suggested measures are: we have to protect the concrete surface by temporary coverings when there is delay between finishing and placing operations. Then number 2, we have to dampen the subgrade. Number 3, we have to dampen the aggregates. Number 4, we have to use as minimum of water cement ratio as practicable. The second physical cause is plastic settlement. As I already told you, the water rises to the surface by the action of bleeding. During this process, there will be a downward movement by the solid ingredients. This descent may be resisted by the top layer of reinforcement or by the formwork. When this occurs, the fresh concrete or the plastic concrete may get separated from the lower surface of the rebars and a void may be created. The cracks due to plastic shrinkage are also quite wide on the upper surface and taper to the level of reinforcement. Some of the measures through which you can control the cracks due to plastic settlement is to use as low a water cement ratio as possible, and we can also think of using microfillers while making concrete. The third physical cause is drying shrinkage. Concrete is also capable of undergoing shrinkage when dry. Drying shrinkage is often caused by the loss of moisture from the cement paste. When concrete dries out, it shrinks. Also due to carbonation, further shrinkage occurs. When this shrinkage is restrained, cracking can result. The cracks due to drying shrinkage can range from fine hairlines to as wide as 3 millimeters. Very often, the cracks due to drying shrinkage serve as entry ports for the ingress of carbon dioxide, moisture and other deleterious substances. Some simple measures to control drying shrinkage will be to use as low a water cement ratio as practicable, using stable aggregates and resorting to proper and prompt curing. The fourth physical cause is temperature movement. Concrete is also capable of undergoing volume change due to temperature differential. Typical visual symptoms of distress due to temperature stresses can be seen in the form of surface falling. Provision of appropriate reinforcement at right place to distribute the stresses and relief joints may help in controlling the distress due to temperature movement. In a building, the trouble spots where the effect of temperature movement is more pronounced include canopies, balconies, parapets, openings, and roof slab. The fifth physical cause is freezing and thawing. Under damp conditions, the pores and capillaries in the outer zone of concrete get saturated with water. When exposed to freezing under this condition, ice crystals are formed. With time, these ice crystals grow. As a consequence, micro cracking is initiated and concrete may also break away from the surface in small flakes, thereby exposing the aggregates. Under repeated cycles of freezing and thawing, even the aggregates may get dislodged from the parent member. Use of air entrainment admixtures is a very effective way of controlling the distress caused by freezing and thawing. The next physical cause is corrosion. Corrosion of reinforcement is a menacing problem which remains to be solved for quite a long time. The corrosion may be uniform or it may be a pitting corrosion. The corrosion mechanism can be attributed to three different processes. The first process is chemical process, where the pH value of concrete is reduced to low value, approximately 10.5 or less, and the passive film formed over the surface of steel is destroyed due to the ingress of chloride ions. The second process is electrochemical process. During transportation and handling, a passive film is formed on the surface of the reinforcement bars, but during working, this passive film gets destroyed. This constitutes the electrochemical process. The third one is the physical process. The products that are formed during the corrosion process occupy volume much greater than the original products, resulting in cracking and spalling of concrete. Some of the important factors that influence corrosion include cover, cracking, carbonation, chloride, and the environment. Environment is very important in the context of corrosion of reinforcement. In IS 456-2000, 5 different categories of environments have been listed in table 3 on page number 18. They are mild, moderate, severe, very severe, and extreme. So depending upon the environment to which the structure is exposed, we have to fix up certain parameters. Some of the important parameters are the maximum water cement ratio, the minimum cement content, the minimum grade of concrete, and the cover to reinforcement. The maximum water cement ratio runs somewhere between 0.55 to 0.4 depending upon the environment, whether it is mild or extreme. The minimum grade of concrete runs between M20 to M40, once again depending upon the environmental exposure. The minimum cement content runs between 300 kg per cubic meter to 360 kg per cubic meter depending upon the environmental exposure. The most important factor which must be looked into is the cover that is to be provided for the reinforcement, especially the tensile reinforcement. Depending upon the environmental exposure, the minimum cover values recommended in IS 456-2000 include 20 mm, 30 mm, 45 mm, 50 mm and 75 mm respectively, depending upon the environmental exposure conditions. Various preventive and protective strategies have been formulated to combat the problem of corrosion. The strategies include coatings to rebars, coatings to concrete surfaces, good construction practice, cathodic protection system, reutilization of concrete, and chloride extraction. So depending upon the degree of damage, the treatment can be resorted to. So before any treatment is taken up, the damage must be properly diagnosed, assessed, and then suitable measures must be recommended. The next cause is abrasion. Abrasion is the loss of material caused due to repeated rolling, rubbing, rocking, or frictional forces. Many factors contribute to the abrasion resistance of concrete. The most important include method of curing, method of finishing, aggregate type, and the service. That is very, very important. Compressive strength of concrete also plays a very important role. The higher the compressive strength, the more is the resistance of concrete to abrasion. The next physical cause is erosion and cavitation. Erosion is the loss of material caused by the abrasive action of fluids containing suspended solids. Cavitation is the loss of material caused by the implosion of vapor bubbles in a high velocity fluid flow. Once the bubbles implode, some energy is released. Because of this, cavitation damage occurs. The cavitation damage results in erosion of the cement matrix. The structures that are more prone to cavitation damage include floor slabs, waterfront structures, marine structures, and hydraulic structures. Some measures to control the impact of erosion include use of high performance concrete, use of microfillers for making concrete, use of tight and smooth forms, avoiding projections, curves, offsets as far as practicable. Creep is also a physical cause which can cause distress in concrete structures. Creep is a time dependent phenomenon. It must be properly accounted for during the process of analysis and design. When it is not properly accounted, load which is not to be transferred to non-load bearing members get transferred to non-load members, thereby causing cracking and other damage. Fire is also an important physical cause which affects the durability of concrete. In general, concrete has good resistance to fire. Of course, it can sustain only up to a certain level. When concrete is exposed to rise in temperature, the water that is contained in pores and capillaries is first driven off. When the temperature rises above 100 degrees centigrade, some of the water combined with calcium silicate hydrates in the cement paste is lost. Because of this desiccation, the strength of concrete comes down. When the temperature is somewhere between 300 and 400 degree centigrade, calcium silicate gets converted to calcium oxide and silica. In this temperature range, concrete experiences an appreciable loss of strength. Further, there is also a distinct color change in this temperature range. The concrete takes on a pinkish tinge in this temperature range. Generally, it has been observed that two types of damages are caused due to fire on concrete. The first type of damage is the explosive spalling in the initial stages of exposure. The second type of damage that is caused by fire on concrete is the rounding off of arises on beams and columns. The second type of damage caused by fire on concrete is the rounding off of arises on beams and columns. Cracks form parallel to the faces and plates of concrete get separated from the concrete member at higher temperature ranges. Steel is also subjected to distress at elevated temperatures. At 400 degrees centigrade, steel retains 90% of its strength. It starts losing its strength only when the temperature is about 700 degrees centigrade. At about 700 degrees centigrade, steel retains only 20% of its strength, but it is capable of regaining its strength upon cooling. Another physical cause is salt weathering. When structures are founded on soil containing brackish water, due to capillary action, this brackish water makes an entry through the weak porous structure of concrete. It starts from the interior and moves towards the surface of concrete. So when it reaches the surface, it gets evaporated, crystallizing salts on the surface. These salts, with the passage of time, can harm the surface of the concrete. Another important physical cause is the seawater. Generally, the effect of seawater is more pronounced only in the intertidal zone. We can have three zones. One is with respect to tidal line, one is the upper zone, number 2 is the tidal zone, third one is the lower zone. As such, the effect of seawater may not be so serious in the upper zone, but at the tidal zone the effect is going to be more aggressive because other disintegration processes also come into play. Some of these disintegration mechanisms include freezing and thawing, alternate wetting and drying, impact by shock waves, and the shock impacted by the floating debris. So far we have seen the various physical causes that can cause distress in concrete. Next we are going to see the chemical causes that can cause distress in concrete. Some of the chemical causes include sulfate attack, carbonation, alkali aggregate reaction, chloride attack, and so on. Let us see the details of these causes one by one. The first one is sulfate attack. The soluble sulfates are more serious with regard to the durability of concrete. The sulfates may be present in water that is used for making concrete or for curing concrete, or they may be present in the soil on which the structure has been founded. Some of the common sulfates are calcium sulfate and sodium sulfate. Magnesium sulfate is not so common, but all the sulfates are more harmful to the concrete. When these sulfates come in contact with concrete, a chemical reaction takes place between the sulfates and the calcium hydroxide as well as the hydrated calcium aluminate, resulting in products like gypsum and ettringite. These solid products occupy volume much greater than the products originally entering into the reaction. As a consequence, expansion is created, disrupting both mortar and concrete, followed by mass deterioration. Hence, it is very important to ensure that the soil or the water is free from sulfates, or if they are present, they must be within the permissible limits. One of the practical measures to take care of this situation is to go in for use of microfillers. Many microfillers are available. Some of them are fly ash, ground slag, silica fume, and rice husk ash. Once these microfillers are incorporated in isolation or in combination in concrete, then the concrete exhibits better resistance to sulfate attack. Super sulfated cement is also commercially available, so that can also be thought of as a measure to take care of this situation. The second chemical cause is carbonation. Carbonation is a simple chemical reaction between carbon dioxide present in the atmosphere and the calcium hydroxide dissolved in the pore solution. Normal air contains lower concentration of carbon dioxide, but in industrial atmospheres the carbon dioxide concentration is more. This carbon dioxide can make an entry into the concrete when the pore structure is very weak by the diffusion process. Because of this ingress of carbon dioxide, the pH value of concrete gets reduced. Normally, when the pH value is 12.5 or more, the steel that is embedded inside concrete is quite safe, which means that it will remain cathodic and the surrounding concrete will be alkaline in nature. But because of the entry of carbon dioxide, the pH value is reduced. As a consequence, the alkalinity of concrete surrounding the steel reinforcement is reduced. Moreover, a protective passive film passed on the surface of rebars is also destroyed. As a consequence, the steel is subjected to corrosion. Hence, it is very important to ensure that the permeability of concrete is very low as practicable. The more the permeable, the more will be the chances for the carbon dioxide to enter into the concrete, and more the chances for steel to get corroded. When concrete is constantly under water, then carbonation will not occur. The rate of carbonation depends primarily upon the quality of concrete. Hence, it is of utmost importance to ensure that the concrete is of good quality. Suppose if it is M20 means it must exhibit good structural characteristics. Even for high strength concrete, the same statement is valid. The third chemical cause which can cause distress in concrete is alkali aggregate reaction. Certain aggregates contain reactive silica which can combine with the alkalis in cement paste forming a rim of gel around the reactive aggregates. This gel is capable of absorbing moisture. So once there is an entry of moisture inside concrete, that moisture is absorbed by gel and it swells, imparting dilation pressure on the surrounding concrete. As more and more water is absorbed, the volume of gel also increases, and consequently the dilation pressure imparted on the surrounding concrete also increases. Initially, micro cracking will be initiated because of this dilation pressure. With time, these cracks propagate, enter into the mortar, and finally they move to the surface of concrete. So this is a very serious situation because the cracks will not remain passive. With the passage of time, the cracks open up, inviting the ingress of other deleterious substances. Hence, it is very important to avoid the aggregates containing reactive silica. The next important chemical cause is chloride. Chlorides can penetrate into concrete from the outside environment, or they can be present in the ingredients that are used for making concrete. For example, chlorides may be present in water that is used for mixing and curing concrete, or it may be present in the aggregates that are used for making concrete, or it may even be present in the soil. Hence, it is very important to ensure that the contents that are used for making chloride are free from chloride, or at least if chloride is present, the concentration must be within the permissible limits. From outside also, chloride ions can make an entry into concrete. Some of the sources are calcium chloride is often used as a accelerating admixture, so that is one source through which chloride ions can make an entry into concrete. The second source is de-icing salts are used on pavements and bridge decks, so through that also chloride ions can make an entry into concrete. The third source is seawater or salt spray. Once again, the more the permeability of concrete, the more are the chances for the chloride ions to easily access the reinforcement. Hence, it is very important to ensure that the permeability of concrete is kept as low as possible. So far, I have highlighted the impact of various physical and chemical causes that affect the durability of concrete. The present day construction scenario is dynamic and multidimensional. In order to have a durable built environment, every engineer should strive hard to make concrete as durable as practicable. In conclusion, in order to make our concrete as well as concrete structures durable, a proper understanding of the various causes that impair the durability of concrete must be properly understood, and accordingly appropriate measures must be taken at the field level. Thank you for the opportunity.